Okay, the format is the same. We will discuss a little bit the setting of the problems, then you try to solve it by yourself, and then we discuss the solution. We again have Andrew, who is there, and Pavel, who is there, who can help you if you don't understand something. I think all of you know what is clustering. Who doesn't know? Very funny. So the clustering is a standard problem in machine learning where you want to you have a set of points and you want to cluster them into several groups. And the most popular method to make clustering is k-means. So the probabilistic analog of k-means is Gaussian mixture model, which says that we have k Gaussians. And we assume that our points are from these Gaussians. So for each point in our set, we have a latent variable zi, and we want to find it to cluster our data. So this zi is a vector of length k, which gives us the probabilities of this point k to point I to be from the cluster 1, 2, 3, and so on. And each Gaussian has parameters mu and lambda. Lambda here is a inverse variance. So it's not sigma as usual, but inverse sigma. This is just a little reminder what is the difference between k-means and Gaussian mixture model. Gaussian mixture model is a bit wider, I think. So in k-means, usually you do hard clustering. So for each point, you just choose one cluster. And usually your clusters are round. So because you have a metric in your space, and usually it's like, for example, if Euclidean metric gives you round clusters. And in Gaussian mixture model, you do soft clustering. So for each point, you find the probability of this point to belong to each cluster. And also your clusters may be not round, but ellipsoid with different covariances. And you may use some priors for parameters of your Gaussians and for P, which is the probabilities of Gaussians of components in the mixture. Is it clear? OK. So this is the most simple Gaussian mixture model. Today we will discuss several variants of Gaussian mixture model. This is the simplest one. Then we will take the more complex one, and so on. If you who already knows what to do with this model? Then you can open a problem set and take the last model. This is the most complex one, so it will be OK for you. And for all other guys, we will go step by step. So our task is to train such model, which means to find posterior distribution for all our latent variables and to find optimal values for our parameters. Do you understand what's different between latent variables and parameters? So what's the difference? You may say it like this, but actually in Bayesian methods, it's your choice. Do you want some variable to be latent variable, or do you want it to be a parameter? So if some variable is a parameter, then you don't use a prior on this variable. If you use a prior on the variable, it's latent variable. Because for latent variables, at the end, you want to obtain a posterior distribution. And for parameters, you just want a point estimate. OK? OK. Before we go to solving the problems, we discuss which methods may be used to solve such problems. You had 3 lectures today, and you discussed at least 3 different methods. So full Bayesian inference on the first lecture, variational inference, actually 4 methods. Variational inference in two variants, like mean field approximation and parametric approximation on the second lecture, and EM algorithm on the third lecture. So when should we use each of them? If we have only parameters, when we just use maximum likelihood, because we don't have latent variables, we don't use Bayes. Okay? If we have only latent variables, what to do? Who knows? Just use the prior. Good answer. But like, does it depend on the prior which method should we use? Prior is not the method. It's like a distribution. We need some method to do inference in our model. Okay, there are actually three, like there are a lot of variants, but we will discuss three of them. Depending on the structure of your model, so the conjugacy of your prior and likelihood, we can choose three different variants. If our prior and likelihood are conjugate, then we just use full Bayesian inference. If they are not conjugate, then we try to find some factorization in which we have conditional conjugacy. If we have conditional conjugacy, then we can use mean field variational inference. If we can't find such factorization, when we need something more strong, and we may use parametric variational inference. Is it clear? So it's like here is the slide, how to choose your method for your model. And what to do if we have parameters and latent variables in the model. EM, yeah. So if we have both parameters and latent variables, then we use EM algorithm. And E-step may be different for different models. So in M-step, we just maximize with respect to parameters. And on E-step, we, again, look at this table and choose a method. So, for example, if we have conjugacy on E-step, then we have standard EM algorithm. If we have conditional conjugacy, then we have variational EM algorithm. Variational EM algorithm is just EM algorithm where you use variational inference to approximate your posterior on E-step. Okay? So this is like a you may have a photo and use it later to decide which method to use to solve your problems. So this is the first problem. How should we train this model, the simplest one? What should we use? Louder. Yeah. Why? That's not true. We have a prior. Let's understand what is the latent variables here. Z, yeah. So here X is observed variable, Z is latent variable, and P, mu, lambda are parameters of the model. So here we have both latent variables and parameters. So we use EM algorithm. And as you will see when you solve this problem, we actually have a conjugacy on E-step, so it will be just standard EM algorithm. So on E-step, we will find posterior distribution for Z, and on M-step, we will optimize with respect to parameters P, mu, lambda. This is the first problem. Like, this is model, and this is what should we do with this model. As a result, we should obtain formulas for EM algorithm for standard Gaussian mixture model. Again, I repeat, if you think that this is like too easy for you, just go to the second problem, or if the second problem is too easy for you, then go to the third one. I think you have like 10-15 minutes, and then we'll discuss at least the first steps. I propose to discuss the first two, like to check that prior and likelihood are conjugate and to do E-step. Okay? What? You finished? You want more time? I don't understand. Go on. So let's discuss first 2 points, and then you will have a little bit more time to deal with the last one. So this is our model. And the first, to check that prior and likelihood are conjugate, you need to take your prior, you need to write down your posterior, and check that they are from the same family of functions. Like as a function of our latent variable z, they're the same. So your prior is equal to this product, and we see that p doesn't depend on z, so we can say that p is a constant, some constant, we don't care about it. To compute the posterior distribution, we use the fact that it is proportional to the joint distribution, and here we also see that p doesn't depend on z, and normal distribution also doesn't depend on z. Yeah. It doesn't matter. It's just like a mistake. Oh my God. So yeah, I have a mistake here and here. It's the same thing. So it's a product with respect to the points. So for E from 1 to n, and the product with respect to clusters for k from 1 to k, big. I'm sorry. I will check my presentations and download the new versions after the seminar. So here they see that p doesn't depend on z, normal distribution doesn't depend on z. So this product of p and normal distribution is some constant for us as a function of z. So we have the same form, but with different constant. So these two distributions are from the same family as a function of z. Therefore, the prior and likelihood are conjugate. Is it clear? Okay. So if we know that our prior and likelihood are conjugate, how to compute the posterior? Okay, we know that the prior and likelihood are conjugate. Which distribution will be the posterior? Like from which family? The same as prior, so it will be categorical distribution. Categorical distribution is just a discrete distribution with some probabilities. So to compute this distribution, to find probabilities of the probabilities of this categorical distribution, we look at our joint distribution and see that we have here some the product of p and normal distribution to the power of z. So in categorical distribution, this thing under the power is the parameter. So from here we know that the probability of z Ekaterina equal to 1 in our posterior distribution is proportional to this product of p and normal distribution. But it's only proportional. We need to normalize them because these probabilities should give 1 if we sum with respect to k. Okay? So we just normalize these probabilities, and as a result, we have the categorical distribution of such form. So here we see that distribution on for each point z e is independent. So we have a product with respect to points, and use these new parameters of categorical distribution in our posterior. Do you have any questions? So it's clear. Okay. Then we should go to the last part. Who already did the last part? Nobody. 1 person, 2 persons. That's not enough. Let's do more. Oh, let's before we you will have more time. Let's start a little bit with the last point, and then you finish it. So first, you on the last point, you need to maximize this expectation of logarithm of joint probability with respect to your parameters. So first, you need to rewrite this expectation as a function of your parameters to understand what to optimize. Let's do it. So first, we see that, so this is what we want to optimize. Respect to parameters p, mu, and lambda. If you look at your joint distribution, which I don't have here, but you have in your problem sets, then you see that we take logarithm, and end up with this sum. Then we use the formula for normal distribution and obtain these two terms. And also a constant, because we have a constant 1 divided by 2p, like a square of 2p in normal distribution. And we don't care about it because it's just a constant. When we use the fact that we know our posterior distribution from the previous step, therefore we can compute the expectation of our posterior. And we denote it as some gamma ik. I'm sorry. And this is the resulting formula, the resulting objective which we want to maximize. Is it clear? Okay. Now, what should we do? Take derivatives and make them equal to 0. And we already did this on the first seminar, so I think it should be easy for you. So let's discuss the M step and at least for 10 minutes go to the second task. So M step, we have our objective here. We want to optimize respect to p, mu, and lambda. When we optimize with respect to p, we see the same thing as we saw on the first seminar. So p is from simplex. Therefore, we have two types of restrictions, the inequality restriction and equality restriction constraint. I'm sorry. So to meet the inequality constraint, we reparameterize our model and use this new parameterization eta k, which is equal to logarithm of pk. And to deal with equality constraints, we write down Lagrangian. This is our function. Like, this is the part of our function which depends on p, this one, the first one. Because the second term and the third term do not depend on p. And this is Lagrange multiplier times our constraint. Then we differentiate and make all derivatives, like the derivative with respect to eta k and c equal to 0, and find the final value for p, which is like quite intuitive since we just compute the sum of probabilities that point E is from cluster K and divide by the number of points. Do you have any questions here? It's very similar to the problem from the first seminar. Okay. And to optimize with respect to mu, we just take a derivative, makes it equal to 0, find the solution. And for lambda, the same thing. And as a result, we have the following scheme. So we have EM algorithm. On E-step, we compute our posterior distribution, our categorical posterior distribution. And on M-step, we obtain new values for our parameters. And we do it in cycle. OK? Do you have any questions? Yeah. Just I don't hear. You said 24. Sorry, no. I thought that I can do it without mic. I don't hear you. If you want to discuss it now, you may go here. Or if you want to discuss it later, we can discuss it later. OK? I just can't hear you. I'm sorry. Do you have any questions which I can hear? Oh, we have a mic. The guy, yeah, in the last row.
Thank you. I was just wondering, shouldn't it be lambda k squared in the first line?
Lambda k where?
You know, it's 1/2 log of lambda k minus 1/2 xi minus mu k squared, lambda squared k. But
now I hear you, but I don't understand you.
oh, so it's a different notation. Okay, okay.
Yeah, lambda is inverse variance.
All right, thanks.
So the second problem is very similar to the first one. The only difference is that we have a prior on P. And as a prior on P, we use Dirichlet distribution the same as in the task at the first seminar. Because it works well for with variables from simplex. So how should we train this model? Like the question one, do we need EM algorithm or not? Yes, that's the right answer. Because we have both parameters, mu and lambda, and latent variables, z and p. The difference from the previous task is that here on E-step, we don't have conjugacy. But we have conditional conjugacy. And you will check it now. Here we should use variational EM algorithm, so EM algorithm with mean field approximation on E-step. So the task is to, like the same as previous one, check that there is no conjugacy, that there is a conditional conjugacy, and write down the formulas for E and M step. For now, I think the most interesting part for us is E-step, because M-step is quite the same as in the first task, and E-step is like a new method on this practical session, variational inference. So I hope we will do at least first 2 points. Yeah. I can explain it in like very simple terms. Conditional conjugacy, like we have prior distribution on 2 variables, z and p, and we have likelihood. If we want to check if we have a conditional conjugacy in our model, we should do the following. We should do 2 steps. First step, fix z, and check that we have conjugacy respect to p, between prior and likelihood, like the usual conjugacy. The second one is fix p and check the same thing for z. That's all. Is it clear? If you want, we can discuss the first part together right now, not later. Let's discuss it together. So we do the same thing. We have our probabilistic model, and we write down prior and posterior. And we can see here that we have this term, some constant to the power of z. We have it in posterior, but we don't have it in prior. Therefore, we don't have conjugacy here. Now, let's try to understand, do we have conditional conjugacy? This is formulas for prior and posterior from the previous slide. Here, C, beta, C dash, C dash, beta dash, and gamma are just some constants. To check that we have conditional conjugacy, first we fix z. And if we fix z, we see that, for example, the last term in the prior is just p to the power of constant, because z is constant now, because we fixed it. It's not a variable. For 1 minute, it's not a variable. Therefore, the prior is just has the simpler form. We don't have z now in the prior. Okay? And the same thing in the posterior. We fix z, therefore the last two terms, the p to the power of z and gamma to the power of z, are both simplified. So we have p to the power of constant and constant. And as a result, our prior and posterior, then we fix z, our prior and posterior are conjugate. Okay? Do you see it? Okay. Then we fix p, so the second variable, and do the same stuff. So we fix p, therefore here we have just a constant, so constant to the power of constant, and here we have constant to the power of z. Here xi is a new constant. And in the posterior, we have also p to the power of beta is now a constant. P to the power of z is now a constant to the power of z. So as a result, we have that we see that our prior and posterior again have the same form, but with different constants. Do you see it? Okay. So now we see that if we fix z, we have conjugacy, and if we fix p, we have conjugacy. Therefore, we have conditional conjugacy. If we have conditional conjugacy, that means that we may use variational mean field approximation in variational inference if we factorize our approximation q for the posterior distribution in the same way in which we checked the conditional conjugacy. So we divide z and p. Now you should do the E-step, like derive formulas for q of z and q of p. So now we understand that, like after this checking of conjugacy, we understand that we can do mean field approximation on E-step. Now we should do it. And to do it, you need this formula from the lecture, the last one. This is the formula how to compute q's. Yeah. What do you mean, local optimization? Local optimization. It's still local optimization. Like when you use variational inference, you still do this cycle and you like find new values for q of z, then new values for q of p, and so on and so on. Like q of z, q of p, q of z, q of p. We don't have time anymore, so we will discuss the solution altogether. If you have a question after this, you can ask after the seminar. So, variational inference on E-step. Variational inference is a iterational process. So we have several iterations. On each iteration, you find new value for q of z and new value for q of p. How to do it? Very large formula, but don't worry. So this is our probabilistic model. Let's first try to find Q of Z. Disclaimer. Since we have conditional conjugacy, that's why we need conditional conjugacy, we will have posterior distribution for Z, so this Q of Z, in the same family as prior distribution for Z. So it will be categorical. And for P, since prior is Dirichlet distribution, the posterior distribution will also be Dirichlet. Now we just need to find parameters of these categorical and Dirichlet distributions. So we use this formula from the lecture. Then we put our probabilistic model under the expectation, and also take logarithm of this of our probabilistic model. And then we see that we have here expectation, and also only this logarithm of P depends on P. So only we need to take expectation with respect to P only from this term. Therefore, I put this expectation inside the formula. Okay? What? Don't worry, we will understand it in 1 minute. For now, it's just an expectation with respect to some distribution which we don't know yet of logarithm of P. So now we see that this is a logarithm of categorical distribution. Remember, categorical distribution is a product of some constant to the power of Z. And here is a logarithm, so we have sum of Z times some constant. Therefore, we say that this part of the equation is a logarithm of rho. I don't remember the name of the letter, rho. Yeah, so this rho is just, we denote these probabilities as rho. And as a result, we have this categorical distribution with new probabilities. Here we need to normalize our categorical distribution the same as earlier. Okay? But we remember that inside this rho, we have this expectation. We put it in, remember it, and we will speak about it on the next slide. Okay? So, the more interesting part. Let's find the distribution Q of P. Here we use the same formula. Again, we put our probabilistic model inside this formula. And we see here that, 1 second. I don't write down the normal distribution here because it doesn't depend on P, and we want to find distribution on P. So we just care about the part which depends on P. So this normal distribution doesn't depend, so we don't use it. Then again, we put our expectation of a Q of Z inside the sum to the only part which depends on Z, Ik. And here again, we have this expectation which we actually we already know how to deal with it because we computed the distribution on the previous step, so we already know the distribution from the previous step, and we can take an expectation of this distribution. Okay? So then I just put everything together and see that here we have a logarithm of Dirichlet distribution. And these are new parameters of this Dirichlet distribution. Okay? So we have Dirichlet distribution with new parameters. Now let's discuss how to compute this expectation of log P with respect to QP from the previous slide. From this slide, we know that Q of P is Dirichlet. And if you open Wikipedia page about Dirichlet distribution, there is a formula how to compute expectation of logarithm of P for Dirichlet distribution. Or if you don't want to use Wikipedia, you can just compute it yourself, like take expectation, take integral, and compute it. It's like computable. The only problem is that since variational inference is iterational process, at the first step, we don't have parameters of Q of P and Q of Z. So we can't compute one of these expectations. So we just want to choose some parameters of Q of P, for example, and use them on the first step. And then after the first step, we already knew distribution on P and Z from the previous step. So everything okay. Here I also have formulas for M step. We will not discuss them. And the resulting scheme looks very similar to the previous one. So we have E step and M step. The M step is absolutely the same. There is no difference from the first problem. And on E step, we have like the second iterational process inside E step with these two steps of computing Q of Z and Q of P. So this is variational EM algorithm. Okay? Do you have any questions? If you don't have any questions, then we may finish and you can go to eat and to discuss your posters. And we hope that you will come back tomorrow.